Hi everybody, this is Mr. Folly, and welcome to Podcast 12.2 Kinetics. We're going to figure out how to determine what steps are rate determining, how to figure out reaction mechanisms, see how catalysts and inhibitors apply to mechanisms, and how to determine whether a mechanism was good or not, and then just a quick review on collision theory, which we've talked about a time or two before. Reactions generally have multiple steps. If it's a single step reaction, it's called an elementary reaction. Individual steps are called elementary steps, and elementary means simple. Elementary school is simple. The slowest step determines the rate. Why? So when you've got different steps, and on my Excel test I have the question, what's the rate determining step for eating your lunch, assuming you don't bring it from home. And the rate determining step is the slowest step because you have to wait in line. So whatever the slowest step is, you have to wait in line before you can do anything else. Or probably a better example is the making cakes example. If I'm making a cake and it takes 2 minutes to make batter, half a minute to stir, and 20 minutes to bake, if I have to make 1,000,000 cakes, the rate determining step is this cake. I have to wait. If I have one oven, I have to wait 20 minutes because as soon as that 20 minutes while it's in the oven, I can make more batter and I can stir it, and then I have to wait for the oven to open up again. So if you want to speed up a reaction, you always want to change the rate determining step. If I find a way to make my batter in 1.5 minutes, the time change for making 1,000,000 cakes is 30 seconds. That's the only effect that it has. If I find a way to change my cake baking from 20 minutes to 15 minutes, then the effect on the rate is enormous. Okay, you always want to change the slowest step. Equilibrium steps determine the rate as well. And that seems weird, and we'll get to that more when we get to equilibrium, but know that equilibrium steps determine the rate as well. We can predict the mechanism. In the past, this was just a best guess. Now we have equipment to help us identify transition states and things like that. Two things must be met to be a good reaction mechanism. That's mechanism. Must obey the rate law, so the rate determining steps add up, and it must fit the stoichiometry. So that means it has to match the balanced equation. Now, does that mean coefficients equal exponents? No. Okay, coefficients do not equal exponents. So for a reaction, CO plus NO2 yields CO2 plus NO. All the species are gases. If my rate law is rate equals K NO2 squared, what that means is, looking at this, my rate determining steps should have 2 NO2s in them and no carbon monoxides. So let's look at the first mechanism. The first possible mechanism is just if it's an elementary reaction. So if you're trying to visualize it, you could see this as CO, and then it's approaching, or plus, and if I write it this way, O, N, O, and you could see how these two could bump, and you could steal one of the oxygens, or actually I should have written it like this, OC, and you can see how this could form a bond and break a bond there, and then you could get CO2 and NO. This does not match the rate law, because if this was the one elementary step, the one step would be the rate determining step, and the rate law would be K CO to the first NO2 to the first, and that does not match up. So that is bad. Possible mechanism number 2 is NO2 is in equilibrium with N2O4, then N2O4 plus CO yields CO2 plus 2NO. And then this is the slow step. Okay, this is equilibrium, so it's got to be rate determining. This is the slow step. Okay, so does this add up? By the way, do you see how N2O4s here would cancel out? This is called an intermediate. Something that is made in one step and subsequently used up later is an intermediate. Okay. So an equilibrium is a rate determining step, and a slow step is the rate determining step. So that means the rate law for this one would be K NO2 squared. That's good, but then I also need CO squared, which is bad. We don't want that in there, so that doesn't work. I could also check to make sure that it will add up to meet the balanced reaction. I would have 2NO2 plus 2CO yields 2CO2 plus 2NO. Now my original reaction had this reduced. Is this the same thing? Yes, because you're going to reduce it in your overall one. So the stoich is okay, or the balanced equation is okay, but the rate law failed. In this case, we have this setup, the step 1, which would be slow, and this is fast, so that means not in rate law. So that means that all of my reactants rate equals K NO2 squared. That matches. And then NO3 is going to cancel out. And I'm going to get my overall reaction then is going to be 2NO2 plus CO yields NO plus, oops, sorry, this NO2 would cancel out, right? With one of these. Would give me NO plus CO2. So that works with the stoich. So this is our best mechanism of choice. You will not be forced to come up with a good mechanism from scratch. You will have to come up with an acceptable mechanism, which we'll practice that in class. 2A plus B yields A2B with a catalyst of C. If the rate law is rate equals KB, if the following is the following reaction mechanism correct? Explain. So if this is slow, this would not be the correct, and this is equilibrium. My rate law from these things would be rate equals, and this gets ugly, K A squared B C. And even though it's a catalyst, it can be in the rate law. Okay. Why is C a catalyst? Because it starts out as a reactant and it is reformed to be exactly the same. What is an intermediate? Something that is formed in the middle. Whoops. Where did that go? I guess that's not it. Something that's formed in an intermediate step and used up later. This one doesn't have one. And I talked about that later. If C was an inhibitor, what's the difference? An inhibitor does what? Slows down rather than speeds up. And you want that sometimes. You want inhibitors to slow down bacterials on your food and things like that. How do these reactions actually occur? Collision theory. This is your explanation for about everything, and we'll see this as we go. Particles must collide. So particles must bump into each other. Even decomposition reactions must collide. Even if it's just hitting the walls or hitting themselves, that's fine. With enough energy, by the way, you can't have too much energy, and the correct orientation. So I think I even mentioned in class how difficult this can be. If you want to have your reaction, you can think of it like a catcher's glove. Oh man, there's a great glove. That's going to catch a ball, right? So the ball is going to go into the glove with the right amount of energy so that the glove will close. Okay. Several possible orientations for a collision between two BrNO molecules. So if your product is supposed to be Br2 and NO. Okay, so this collision right here, you can see how these two could collide, and then these two could be split off. Okay. Looking at this, you can see how these two can collide, and these two can break. Looking at this orientation is bad. Now realize, molecules don't just collide at 90-degree angles. We've rotated this. They collide any way they want to. So these are two different things. Most collisions are unsuccessful, and that's important to know. And depending on the reaction, oops, this should be full. Depending on the reaction, sometimes 1 out of 10 to the 12th is not abnormal. Wow, so think about that. So how do these reactions ever happen? We're talking about moles of particles here, which are 10 to the 23rd. So many collisions that even though the success rate is so low, they still have an appreciable amount formed. Mechanisms are predictions. There's no one specific answer for AP chemistry. So that means we can create our own as long as it matches those things. Rate is determined by experiment from the previous podcast. Don't forget that. Mechanisms must obey the rate law and stoich. I think I might prefer balancing for that, even though they're my words. Catalysts, inhibitors, and intermediates are involved in the reaction, but they are not reactants, nor are they products. Defining collision theory is the explanation of why rate changes. More next time on that. One thing I didn't mention to you is that K is constant. K is a constant. It's always the same unless you change the temperature. So that's kind of a nice thing to do. The last thing I'll tell you is look on your equation sheet, and I should have one in it, for a reaction for a rate law thing that has EA in it. You need that for class tomorrow, and we'll talk about that. I'll show you how that is a, that's going to be the question I'm going to ask is what is the EA equation on your equation sheet. Have a good one, and we're out of here in a decent amount of time. Woohoo! Bye.